Don't let me know if you
think it's recording. Yeah.
Great. Okay.
Oh shit.
What's not going
Okay.
well? Hi everyone. Hope you're having a great weekend so far. So glad you decided to take some time out of your lovely day today to come see us. So, hi everyone. I'm Rachel,
I'm Kate.
and we're going to be going over some exam 2 content for your exam coming up on Wednesday. So, we'll essentially just start by going through some general notes on stuff. We have some practice problems for you guys. Any questions you guys have, please ask throughout the presentation, and hopefully we'll have some time at the end to go over questions as well. Yeah, any questions on any of that, I guess? Awesome. Lit. Cool. All right. So,
Do you want to move it?
yeah, actually, great. Thanks. Thank you. Should you? So the first thing we're going to start with is we're going to start going over memory lists and mutability. So when we think about setting variables in Python, variables don't necessarily hold objects. You can think of them more as holding references to objects. So thinking of variables this way is super crucial when we're talking about data structures and recursion. So we have a couple of different types of variables we might be setting. We have primitive types, which are integers, strings, and booleans. All of those you may remember from exam 1, and they are immutable, which means we can't go in and change those values. However, we have a couple of values in this course that are mutable. Lists and dictionaries are the primary examples of that. That essentially means that they can be changed. Any questions on any of this so far? So just as a quick intro, when I say variables hold references, I like to draw it out in this kind of way. So let's say we have a variable L, we're saying it equal to a list. Instead of saying like L equals a list, what I like to do is I'll make a linked list. So we'll do the string 42, high, and 12. I don't know what list that's for. Think of the variable as holding a reference to that list. So rather than thinking of that L is the list, L holds a reference to that list. So anytime we're referring to L, essentially we follow that arrow and we go straight to the list. This will make more sense when we talk about aliasing as well. But any preliminary questions on any of this? Cool. So if two variables point to the exact same location in the computer's memory, altering the structure through one variable will immediately affect the other. So this is why passing a list into a recursive function is usually pretty detrimental because mutating it will affect the list everywhere. So to avoid this, we have to use copies of lists. So this is just a general thing when we're talking about recursion. If we're using lists, we want to make sure we're using methods that do not change the list directly. This has to do with aliasing as well. So let's say I set L equal to this list, and then I say A equals L. What that does is we have a new variable A that's now pointing to the same list. If I make any changes to L, so if I say L dot append and I add, I don't know, 2 on the end, that means I'm making the same exact change to A as well because A and L are pointing at the same list. Question so far? Cool. All right, so in that same vein, we have destructive and non-destructive operations. So our destructive operations are essentially mutating an object directly. So they don't create a new object. They mutate that one directly, and they usually return none. We have one exception to this that we might use in this course, dot pop. Dot pop, when we take out a value of a list, it'll return that value. So that's one of the exceptions where it doesn't return none. But typically, some of the immutable options that we have, such as l.append or list.remove and list.sort, these are all destructive and they return none. Non-destructive essentially are things that create a new object. So if we set list equal to 1, 2, 3, and then we say new list equals list plus 4, this concatenation is a non-destructive method. So it creates a new list that includes 4 on the end that has nothing to do with the original list. So what we can imagine is we have our original list is we are pointing to a list with 1, 2, 3. Our new list points to a completely different list. If I said list.append 4, that means 4 gets added directly to this list. but our new list points to something entirely different. So that's essentially what it means to be non-destructive. So we have some examples of that. We have the concatenation here. We also have the function sorted. So you can see there's a comparison between using list dot sort, which is a destructive function, and list like sorted, which is a non-destructive. And then any list slicing is also non-destructive, so that will return a new list. And just as a reminder, non-destructive methods are super important for recursion. Questions? Awesome. All right, so let's talk aliasing. Take a minute. Yeah, take a minute to look through this code and think about what's going to be printed in these three print statements at the bottom. And then at the end of it, which lists, if any, are aliased. So take, I'll say 30 seconds now to look through that, and then we'll go over it. Yes. No, that's, I should have
I
noticed.
didn't even notice that.
I like literally.
Hmm.
I don't know if that's the right way to put it, but we're gonna use it, but it's working, so fine. Kind of working. Oh, maybe it's this. Nope, that's even worse. All right. All right. So here's how I think about this code. We're starting and we have a variable A. We're setting that equal to a list. 1, 2, 3. Cool. So we have an arrow there. Now we say B equals A. So we're going to introduce a new variable that's pointing to the same list. Now we say B dot append 4. Thumbs up if B dot append would be a destructive method, and thumbs down if it would be a non-destructive method, based on what you guys remember from the slides. Yeah, great. I'm seeing a lot of thumbs up. So that would be a destructive method. So we're just going to throw this off and add 4 on the end. And now we're going to print A, B, and A is B. So we print A, which is 1, 2, 3, 4. We print B, which is also 1, 2, 3, 4. And then this is operator essentially says are A and B the same thing. Hopefully, by now we can see that A and B are the same thing. They're pointing to the same list. So that would print true. Questions on any of this? Yeah.
The dot, that automatically destructive.
For the most part, yes. Yeah. So if you see the dot, just assume it's destructive. I can't think of any examples, no, but I don't want to make a blanket statement in case I'm losing something out. All right. And then really quickly, let's go through these and discuss whether they're destructive or non-destructive. So we'll say thumbs up if they're destructive, thumbs down if they're non-destructive. All right. List.sort. Yep. So that one's destructive. Okay. Sorted. Non-destructive. Dot append. Yep. Destructive. The concatenation. Exactly. Non-destructive. And then dot remove. Yep. That one's destructive. And then any slicing. Non-destructive. So this is also like ordered so that each pair of lines is equivalent in terms of what it actually does to the list, but the methods are either destructive or non-destructive, so they're going to be used for different purposes, whether we're using them for recursion or direct mutation or something like that.
If you then move 0.
Oh, I see what you mean. So technically remove and then dot pop are different things. So remove removes the value itself. Technically I guess it should be remove 3, I think. I don't know why we're removing 1. So technically I guess, okay, let me reword this because we're appending 5 versus adding 6. They're not doing the exact equivalent thing, they're doing the same idea. But dot remove would remove this 1. And then the slicing would just have the 3 cut off at the beginning. Okay, final questions on lists, aliasing, mutability. All right.
Slide. So now we'll move on to recursion. I'm sure this is a topic everybody loves. So there are 3 essential ingredients to writing a recursive function. The first one is the base case. This is incredibly important. This is like the simplest irreducible form of the problem. So if we don't have a base case, our problem is going to keep going forever. So whenever we start with a problem, the first thing that we want to do is just sort of think about like, what is the smallest problem? Sometimes it's easier to like write the recursive case first and then go back to the base case, but it's important that we have one. And usually it's pretty standard, like it would be the empty list or the empty string or an empty dictionary, whatever it happens to be. But keep in mind that that is not 100% always the case. Like sometimes our base case is not just going to be the empty list. It is just the smallest case of the problem. So it depends on the problem. But if you have to guess, you can guess. And then the recursive case is when the function is calling on itself to solve a smaller piece of the problem. So I guess people think about this as like magically working. I would agree. This is just like a leap of faith. You're just going to assume that your function is doing what it's supposed to do, and you're just going to deal with one step of the problem and then tell your function to deal with the rest. And the assumption is if you are dealing with a smaller step, then your function is going to deal with all the individual smaller steps, which will combine to solve the whole problem. And then the next important thing is to move towards the base case. This is also incredibly important. So every call that you make, it needs to be shorter. You can't call your function on the same exact input every time, or else you'll never reach the base case. So you're just gonna like recurse infinitely. And this is sort of like the same idea as like an infinite loop. So like your code is just never gonna end. Questions on this? Okay. So the logic of a single call recursion. So one way that you can approach it is to process exactly one character or item and then delegate the rest of the function. So in this one, we have count vowels as an example. So in this one, we're designating smaller to be our recursive call. So we are slicing it. So we're chopping off the first element of this. I'm going to assume a string or a list. And then we're calling our recursive function on that. And then our work is that we're just going to check if the first index is a vowel or not. And then we're going to take care of that, right? If it is a vowel, we're going to add one because we want to just be like, okay, this one is, count the rest. If it's not a vowel, we just return smaller. So this is essentially us saying like, don't include this in the final count. And then the way this is going to work is it's going to propagate up, right? So eventually we'll reach the base case, which is 0, and then we'll just start adding each individual layer. So the kind of steps that you can take to write a recursive function is to define the base case, isolate the first element, make the recursive call on the rest, and combine the results. And sometimes combining the results doesn't necessarily mean like plus. It can be like a Boolean or anything like that, but you just have to combine the result in some form. So one way that we can think about it is the bookmark method. So this is for recursive tracing, right? Tracing recursive functions. So what we want to think about is that each function call essentially places a bookmark on what we're doing and waits for the nested call to finish. So for example, if we think about this example at the top here, we're going to call on fact 3. And then fact 3 is going to call fact 2. So we're going to be like, okay, stop. I don't know what fact 3 is. I need to figure out what fact 2 is. So then we're going to call fact 2. But then fact 2 depends on fact 1. So we're essentially going to keep doing this until we reach our base case. And once we do reach the base case, we propagate the values forward. That just means like we're going to return each call down so that they can like do the combination that I was talking about before. So if you're ever trying to do code tracing on a recursive function, I would highly recommend that you do something like this. You don't have to draw it in this way, but some like way, shape, or form that you're sort of like stopping and telling like what your function is depending on, and then you can like add up the individual results. And then multi-call recursion, this is sort of like the Fibonacci sequence. If you guys are unfamiliar with that, it's just the addition of the previous two numbers in the sequence. This is not very common, I will say, but it's just like the recursive function is making like more than one recursive call. So this is sort of more of like a tree structure. So if we think about it, like every time we want to calculate the Fibonacci number, we will not need to do 2 recursive calls. And then each one will also call 2 things. So that's why we think of it as a tree, because it's sort of branching down. It's not just like one call. Also keep in mind, we're doing n-1 and n-2. So now we need 2 base cases. So whenever we have like multiple recursive calls, it's not necessarily that if you have 2, you're going to have 2 base cases, but in this case, because we're doing n-1 and n-2, then we need to case for 2 different things, right? Because if we only case on one, we might reach 0. And since that wouldn't be a base case, we would start going into the negatives and then we would just recurse infinitely. So that's what I mean. Like the base case is not always just like 0 or empty list. You just kind of have to think about the problem and like the smallest thing that you want to consider. Questions so far about recursion? Okay. And then there's also some complex functions. If you guys remember Towers of Hanoi from the lecture slides, this is not something that you would be expected to code on an exam, so don't worry about that. But this is just sort of an example where it's like using recursion makes this problem infinitely simpler because if we were to do this like iteratively, which means like with a loop, it would be like a lot harder, right? So whenever we're using recursion, we can just sort of make like two recursive calls and that will sort of solve our function for us. So some problems are just naturally recursive. So again, if this doesn't make like 100% sense to you, like that's okay. Like you're not going to be expected to code something this complex on an exam, but it's just an example of like how recursion can be used to simplify problems. So, okay. Now we're going to do an example. We want to write a recursive function that is going to return the sum of all the elements in the list. And I will say, like, on exams, like, we will most definitely, if we want it to be recursive, we're going to say, like, don't write a loop. And if you do write a loop, you're going to get a 0. So always try to solve something recursively. Like, if it's telling you to be recursive, don't write a loop. Just, like, try your best in writing a base case and a recursive case. But I'll give everyone, like, a minute or so to think about this problem. Okay. Did anyone share what they did for their base case? Yeah. Yeah. So there's two ways to write this. You could case on the length being 0, or you could do if L equals the empty list. They both mean the same thing, but yes. And in this case, what do we return? Yeah. Yes, 0. So going back to your empty list, if we did return the empty list, that would cause issues because remember what I said about propagating forward, right? So ret sum needs to return an integer. So that means everything we return has to be an integer. That's actually an important concept in recursion. So every single one of your return statements should return the same type. So just yeah. So if your recursive case is going to return an integer, then you should always return an integer in your base case as well. Thank you guys for sharing. So now we're going to go into our recursive case. So we can sort of split this into a smaller problem, which is going to be, I'm just going to call it smaller. We're going to deal with the first index of the list. And then the result is going to be us calling our function on the remainder of the list. So it's L of 1 forward. So what do we sort of want to return in our recursive case?
whatever term. The sum of, split up list plus the first element of the list.
Exactly. So,
Sorry,
yeah.
I said like a counter equal to 0, and I said counter like plus equals, or is that not? If we're trusting the function to do what it does, do we not have to set it as plus equals? Something?
well, you could do that, and then your counter could be like L of 0 plus rec sum of whatever, and then you can return your count.
I said counter equals 0, I said counter plus equals sum of lists, like the small result, and then I just turned counter plus list as 0.
Yeah, I think that could work. Just be careful because sometimes the order matters. Like sometimes we want this to come before this or like vice versa. So like you could take that approach, but I think it's risky because like variables don't transfer into recursive calls, if that makes sense. But if that makes sense to you, that's okay. But I would say like if you're to be safe, I would sort of always like return the work in the return statement itself. So in this case, we would return smaller plus smaller res, which you can simplify to just being L of 0 plus rec sum L of 1 forward. But yes. So like sort of the thinking here is if we have an empty list, obviously the sum of that is 0 because there's nothing in it. Otherwise, we will consider the first value and tell our function to sum up whatever the remaining values of the list are. And then whatever that happens to be, we just add the value now, and then we have the total sum. Any questions? Okay. Lovely. So now we're going to trace through this function. So I will give everybody like 2 or so minutes to think through what it's doing, and then we will trace through it together. Okay. So whenever we call mystery of hello, or okay, whenever we approach a recursive function, we always want to just think like, are we at the base case or not at the base case? So in this case, we're given hello. It's not an empty string, so we're not at the base case. So we're going to fall into the else case, which means we're going to return mystery of hello plus our h, right, which is s of 0. So this is what I mean by the bookmarking thing. So the way that I like to think about it is I'm going to write out my recursive call plus whatever I have. And I'll keep doing this down, right? So whenever we have mystery of LO, we're going to call mystery of LLO, right? Plus the E. And then this is going to call mystery of LO plus the L. This is then going to call mystery of O plus the other L. And then this one is going to call mystery of the empty list plus O. And then finally, we reach our base case, which means we return the empty list. So we sort of have to sum everything back up, right? So always start down up. So the empty list plus O is just O. And then this O is this thing, right? So now we have to do O plus L. And then we're gonna add O, L plus another L. And then O, L, L, the E. And then finally O, L, L, E, H. And then that's what's gonna be returned to our main call. So this function is just reversing our string essentially. But that goes back to what I meant about the order. So like in this case, it did matter like the order of like when we added our result and how we had our function, because if we flipped it, then we would just be getting the same exact string back. So we just have to be careful about the order that we're adding our inputs. And whenever we're like adding or multiplying, it doesn't matter, but if we're like subtracting or dividing, then it starts to matter, like the order that we call it in. Do we have any questions? Okay. There we go. So now we're gonna get into big O.
Alrighty. So, big O notation measures how the runtime of an algorithm scales as the input approaches infinity. So essentially the goal of big O is to represent how efficient a function is based on the input size n. So we usually drop the constants in the smaller terms and we focus purely on the dominant growth family, which gives us a couple of different runtimes that we're going to focus on in this course, and I will write them out on the board right now. So we're going to start with O of 1 constant runtime. Then we have O of n squared. We have log of n. Then we have 2 to the n. Or by extension, sometimes we'll see this as like k to the n. We also have O of n to the k. And O of n factorial. Hopefully these are all big O function, or not functions, runtimes you guys have seen before, because they are all ones we've discussed in class, but these are generally the ones that we'll see. So we split these into basically two different families. We split them into like reasonably efficient or tractable and sort of inefficient, I guess, or intractable. And that's sort of shown on this graph. We have like different colors showing how efficient the different functions are. So these are our functions. As you can see here, we have log of n, O of 1, and O of n. These are all in the green and yellow range, which means they're reasonably efficient. This also includes any polynomial function. So in addition to O of 1, O of n, and O of log of n, this includes any function where n is the base of the exponent. So this sounds kind of stupid, but O of n to the 1 millionth technically is considered a polynomial function, so it's considered reasonably efficient. Everything I haven't just boxed is considered not very reasonably efficient. They're not polynomial functions. They're going to be in this red range up here, which means we want to try to avoid them when possible if we're thinking about runtime. So if we're looking at code, there are some different ways we can determine the big O runtime. So for example, we just have this loop for I in range length of list. Again, we're assessing our runtime based on the input size. So here, if we're assuming that our list has length of n, we would just say that this loop is going to run n times, so that gives us O of n. Versus in this example, we have two different loops and they're nested. So in that case, we have two loops and each one is O of n. So we'd multiply those together to get O of n squared. Just as a recap, we have rules when we're doing big O notation. So subsequent lines in code, we add. Subsequent lines, which means lines that are like indented at the same length, add runtimes. And nested lines, so if they're indented within each other, we multiply times. So that's where we get this nested for loop. That's where we get O of n squared, because we're multiplying the two runtimes of O of n. So when we're looking at runtime, we have to sort of standardize how we're assessing the speed of the algorithm. So it depends on the exact input provided, not just the size. And we essentially analyze the bounds of that input. So if we're talking about a list and we're running linear search on that list, you guys may remember from recitation, we went over that linear search is an O of n runtime because in our worst case scenario, if we're looking for an element in the list, we have to check every single value in the list. So we have to check n values. If we were considering our best case scenario in which every time we get a list, the value we want is the first item that we're checking, that doesn't really tell us anything about how efficient the function is because we're assuming the function always works as efficiently as possible, which isn't really the case. So we assume the worst case when we're calculating runtime. So in this case, the target is either at the very end of the list or doesn't exist at all. Technically, it's more correct to say the worst case is that the list does not contain the target element. And the loop runs all n times, so that makes it the worst case scenario. Any questions so far? All right. So comparing linear and binary search, you guys may remember we did a bit of an in-depth comparison during our recitation like a couple weeks ago. As I mentioned, linear search in its worst case is O of n because we check every element sequentially from start to finish. Binary search, we call it binary because it splits our list in half every time and then checks only half of the list. So you can think of our big input n and we essentially divide it each time, which is a logarithmic runtime. Oh, and just as a reminder for binary and linear search does not have to be sorted, binary does. So we have some functions here. Take about a minute and go through and try to calculate the runtimes for each of these functions, and then we'll go over it. Mm-hmm. Yes. Hmm. Oh, yeah. Okay. That's a great point. There might be stuff in here that we haven't seen. So thanks for pointing that out. So with code D, just a couple of quick FYIs. You don't need to know this, so don't worry about it. If we ever set variables like this, low, comma, high, it essentially is a way of setting two variables at one time. So all you do is set low equal to 0, high equals to length of list minus 1. You are also technically allowed to not indent after an else statement. Like you can keep everything on the same line with these if, elif, and else. It's just the same thing as you can imagine else, indent, high equals mid minus 1. Does that answer your questions? All right. Can anyone tell me what the runtime? It's only one line, so hopefully this one's pretty self-explanatory. The big O runtime for function A would be. Sorry, what was it? Exactly. Yep. So n times 2. It doesn't really matter assuming it's a number, it doesn't really matter what n is. We just always multiply it by 2. Doesn't matter if n is 1,000, doesn't matter if n is 1. We just do one step the whole time. Okay. What about B? Yeah, exactly. So that's going to be O of n or linear because we just print every value. So it depends on how long our list is. All right. C. We have two indented loops. This looks really similar to the last slide. So what are we thinking for that one? Yep. So that would be n squared, just the same thing we discussed on the last slide. And then lastly, binary search. You don't even have to look through the code for this one. What is the runtime for binary search? Yep. So just some recap for that. Any questions on calculating runtime? Yeah. The slides? So the recorded version of this will be online. We typically don't release the slide deck in itself. Orly, do you have a question?
as far as like using that only for binary search, or are there other, do you have other?
Yes. All right. All right. So I wrote this function, it's called function of n, very fun name. So we're assuming n is a number. If we pass any number into this function, our goal here is, while n is greater than 0, we're going to print high and divide n by 2. So if I plug in the number 32 into this function, okay, we start with 32. I'll write a little table here, and then we'll say printed. We start with n equals 32. We're going to go into this loop because n is greater than 0. We are going to print high, and we are going to divide n by 2, so we're going to get 16. We're going to go back up to the top of the while loop. We're staying in this while loop because n is still greater than 0. So we're going to print high again and divide n by 2 again. We're going to keep going. So we're going to print high again, divide by 2. Keep going. 1. High. Now we've hit n equals 0. Here's an example of a logarithmic runtime that does not have anything to do with binary search. Because our input, every time we double our input, I'm printing 1 extra high. So if I double this from 32 to 64, our function doesn't take double the amount of steps. It only takes 1 more step because we're only going through the loop 1 more time. Does this make sense? Do we have any questions on this? All right. And then we did go over this, so I'll just say briefly for a linear search on n elements, we know the best case is if we find the item in the first part of the list, which would make it a constant runtime. And the worst case is we're looking through the entire list to find the element and we don't find it at all. So that would be O of n. And when we're talking runtime, we usually report the worst case, not the best case, because again, the best case doesn't really tell us anything about the actual function. All right, just get that. All right, we'll move to dictionaries now.
Okay. So the power of dictionaries is that we store data in pairs, right? So unlike the lists that we have a list and it has a bunch of values in it, with dictionaries, we can have a key that maps to a specific value. So these are very useful for counting frequencies. So the main benefit of a dictionary is it's efficient, right? So whenever we have to search, it's constant time versus a list where we have to look through everything. And we'll get into this in a second. But you can iterate over dictionaries just like a list. You can do like for key in dictionary. Just note that dictionaries don't have order. So like you don't really it's not going to be that apples comes before bananas, right? Like he could be bananas and then apples. Dictionaries don't really have a specific order. They're just like there. But it will iterate through the whole thing. And why are dictionaries fast? It's all about hashing. So lists use linear search to find values. Whenever you guys do like, oh, if I is in list, that is using linear search, which is why it's O of n efficiency. But the dictionaries use a hash function. So essentially, this just means that it takes the key of the dictionary, it hashes it with some mathematical calculation, and it's going to put it in a bucket, right? So essentially, what we have is whenever we do like, oh, is like K in the dictionary, it's not going to search through the entire dictionary. It's going to take K, do the mathematical thing to it, and be like, okay, if this were to be in it, it would be in bucket 1. It's going to look in bucket 1 and be like, it's not there, it's not in the dictionary, and it's not going to look through anything else. And this sort of brings up the point about collisions. It might happen that we have multiple things in this bucket, right? Like we might have 2 keys that hash to the same value, but most likely it's like not going to be that many things in the bucket. Like, so it's still going to be constant time because it's going to be a constant number of things in the bucket. So overall it's going to be O of 1 average time complexity. Because remember with big O, like we don't care if it's like O of 10 or O of 20, like that's just O of 1 because it doesn't depend on the length of the dictionary itself. So do we have questions about how dictionaries work and why they're fast? Okay. So the key constraint is that we cannot hash mutable things. So for example, a list is mutable because of the reasons we talked about before. You can pop things, you can append things, they're going to change. So we can't really hash that because the hash value is going to depend on what the list is at the beginning. If we change the value of the list and then we try to unhash it, it's going to lead us to a different bucket, right? So we're going to be looking in the wrong place. So we might like say that it's not there when it actually is because we're going to be looking in a different bucket. So we cannot hash lists, right? And thus, that means we cannot have mutable values as the keys of the dictionary because dictionaries require the keys to be hashed, right? So whenever we have dictionary keys, they have to be immutable, such as strings, ints, floats, booleans, tuples, whatever. So they cannot be lists. They can also not be dictionaries themselves because dictionaries are mutable. The entire dictionary itself is mutable because like you can add the values or you could like change what a key points to. So the keys of the dictionaries are immutable, but the dictionary itself is mutable, which is confusing, but yes. So we want to write a function count chars that returns a dictionary mapping each character to how many times it appears in the string. So for example, with banana, B is there once, A is there 3 times, and N is there twice. So I will give everyone like 2 or so minutes to think through how we could write this function, and then we will write it together. Okay. So let's think this through. So I'm going to change this to S actually. We're given a string and we want to make a dictionary. So usually the first step is to initialize an empty dictionary. So we can do the little curly brackets. You can also do dict parentheses. Either ways are fine ways to initialize a dictionary. Up to you. And then now that we have our dictionary, we are going to go through S, see if the key exists. If it does exist, we can add 1 to it. If it doesn't exist, we can set it to 1, right? So we're going to do for C in S, which is for char and string, if S in D, or if C in D, what are we going to do? So if this key already exists in our dictionary, what should we do?
Add 1.
Exactly.
DSC.
Yes, so DSC plus equals 1. Otherwise, we're going to initialize it to 1. So if it's in it, add 1. If it's not, d of c is now equal to 1. And then at the end, we can just return d. Any questions? Okay. There we go.
You have to return. Oh, yeah.
Yes, we have to return d. Okay. Now we're going to go through this and see if we could use these as the dictionary keys. So we can just do thumbs up if it can, thumbs down if it can't. So 42, can that be used or not? Okay. Yes, it can be used. Ints are fine. What about the string hello? Good. What about the list 1, 2, 3? No, right? Because lists are mutable, so they cannot be keys. So I realize you guys may not have seen this, so we can skip it. But it's just like a tuple, but there's 3 things in it instead of 2. They are not mutable. You can't change tuples. So if knowing that, can they be keys or not? Yes. And then we have the dictionary containing A1. Yes or no? No, right? So it's funky, but you can't use the dictionary as a dictionary key because, like I said, dictionaries are mutable because we could change it, we could add 1 to A. And then what about 3.14? Yes, that's fine. It's just an integer and the value true. Yes, booleans, you can't change them. So yes. Questions? Okay. So this sort of goes back to what we were talking about before, but why is looking up a key in a dictionary O of 1 on average, and why is it looking up in a list O of n? So it's because of hashing, right? So because we can hash the keys in the dictionary, we can just look them up in the buckets. We don't have to go through the entire dictionary itself to find if something is in it. Versus in a list, we do have to loop through the entire list in the worst case to find if something is in it. Any questions about dictionaries or hashing? Okay. There we go. So now the last thing is trees.
All right. So, to talk about trees, trees are hierarchical data structures that start from the root node and branch downward by the edges to the leaves. These are nodes with no children. So trees are, we call them naturally recursive structures because naturally they are like each node has a sort of subtree below it. So for example, if we take the root node in this tree right here on the left, it has 2 subtrees, one with the node of 3 and one with the root of 3 and one with the root of 10. So we call that a naturally recursive structure, which means anytime you see trees on a homework exam, whatever, you're probably going to have to use recursion if you're doing any coding. A binary search tree maintains 3 rules. So every left child has to be strictly less than its parent node. Every right child is strictly greater than its parent node, and the rule applies recursively down the entire tree. So, for example, we have this right here because we have duplicate values. Technically, it doesn't count as a binary search tree because we say the left children and the right children have to be less than or greater than. There's no equal to. So technically, BSTs cannot include duplicate values. This one also, we have an example where this node here, 7, is to the right of 8, but it's less than 8, so that violates. And then right here, we have another example where this node in the 9 is, yes, it's greater than 6, but it is less it's greater than 8, and since 9 is on the left side of 8, it should all be less than 8. So that's what it means when this rule applies recursively down the entire tree. And as a reminder, it's called a binary tree because each node would have max 2 children. Questions on any of this? Here's an example of the way you might see a tree represented as a dictionary. So we usually represent it as 3 different terms. We have contents left and right, where contents is a certain node. So this would say that our root node is 6. Then we have nested dictionaries where the left and the right trees are equal to essentially smaller trees represented as dictionaries. So I have a question for you guys. Kate was just telling you about how we can't use dictionaries in dictionaries. Why am I allowed to use a dictionary here? But it's still a dictionary. Why am I not allowed to use it? I'm sorry, why am I allowed to use it? I phrased that poorly. It's not a trick question. You are indeed allowed to do this. It's not me trying to trick you guys. Exactly. Yeah. Right on the money there. So we can't use dictionaries as keys because keys can't be mutable. Yes, keys can't be mutable because they have to be hashable. But here we're using them as the value because our keys are just strings. So that means we're allowed to do this. Questions on any of that? So linear and binary search in trees, if we're using linear search on a tree, you can kind of imagine because we've said a tree is a naturally recursive structure, this kind of doesn't really make that much sense. We have to check every single node in the tree, which is kind of boring and annoying. That runs in O of n runtime. However, with a binary tree, if we're taking a binary search tree, it's already sorted, it's already binary. That makes it really easy to search because we essentially just decide which half of the tree to look on based on looking at a certain node. So if we go back to this, let's say we can imagine this tree just don't have the duplicate 4. Let's say we're looking for the value 1. We can look at our root node of 8 and we'd say that, well, our target value of 1 is less than 8. So we only want to recurse over this subtree. And we can just keep cutting it down that way, which is essentially exactly what the binary search is meant to do. All right, so as a recap, I showed you guys that trees are nested dictionaries. We have contents left and right, so we have contents with the node's value and left and right for the subtrees. Here's an example of summing the nodes on a tree. We essentially, for our base case for trees, are usually checking if the tree is equal to none, and in that case, we want to return 0 because for a sum, we should return an integer no matter what. And then in this case, we're going to sum both halves of the tree because we have to remember that with a tree, we would have 2 halves with a binary tree. So we want to account for both those halves when we're summing all of the nodes. So we have 2 recursive calls here, 1 for each side. Questions? All right. Graphs are also represented as dictionaries. So we have an example here, and how these ones are represented is we have a string with a node, then we have our colon, and our values are essentially lists with a combination of the nodes that are neighbors as well as the weights of their edges. So this obviously assumes our graph is weighted, and as a reminder, that means our edges have values or numerical values. So in this case, it's essentially telling us that A has neighbors B and G, and the weights of those are 5 and 2. And then we have B has neighbors C, and the weight of that is 3. Something you might also notice is that A and B are not in each other's lists. So A has B as a neighbor, but B doesn't have A as a neighbor. Does anyone have any guess what this might mean in terms of a graph? Yeah. Exactly. So it's directed, so we'd have an arrow going from A to B, showing that they're neighbors, but this arrow would not be double-sided. It would not be going back to A. All right. Now let's talk brute force and tractability. So this kind of goes back to our runtime. When we're solving a problem, sometimes we have the solution of the problem. We don't know how to solve that in a quick way. We can't find some O of n or O of 1 solution to a problem. And in that case, we use a brute force algorithm. So that's essentially solving a problem by explicitly checking every single possible solution. So an example is the traveling salesperson problem that you guys might remember, which is essentially we have a collection of cities and we want to try to find the shortest route between all the cities where we visit each city once. So in that case, we'd have to check every route between every city. Yikes, that's O of n factorial. That is not a tractable runtime. So we know from before that non-polynomial runtimes such as O of n factorial are not tractable, which means it requires exponential or factorial time. Large data sets physically will not be computed for these problems. So if we do traveling salesperson with all of the cities in a state, for example, that would take a ridiculous amount of time, and we would not be able to find a solution to that. So we're introducing P and NP. P are problems that can be computationally solved and verified in polynomial time. So we know how to find a solution to the problem in polynomial time, and we know how to verify if that solution is correct in polynomial time. Versus NP, we know how to verify a solution is correct in polynomial time, but we don't necessarily know how to solve it in polynomial time. So an example of that is subset sum. So we have a list and we have a target number, and we want to see if there are any subsets of that list, so any smaller list containing any of those list values that add to the target value. Obviously, if we have a solution to that, it's very easy to check it. We can just sum up all of the values in that sublist, and we can see if that equals the target value. That takes about 2 seconds. That's tractable. But we don't necessarily have a solution to that to solve in an easy way. So when finding the perfect solution takes too long, heuristics are a way of finding a good enough solution quickly. So if we're talking traveling salesperson, you guys did this on your homework where we just picked the path where you're always traveling to the city that is closest from the one you're currently on. Do we know if that's the shortest solution? We don't, but we're just using that as a heuristic to come up with a quick answer. A couple of quick problems before we finish up. We're going to do thumbs up if this is about a valid binary search tree and thumbs down if it's not. So is tree A valid binary search tree? I'm seeing some thumbs up, and yes, it is valid. Again, we just checked that all of these values are less than the root and all of these values are greater than the root, and we would check that for all of the subtrees as well. Okay, I'm going to give you a hint. Tree B is not a valid BST. Can someone tell me why? Yeah, because the 9 is to the left of the 8, but 9 is greater than 8. Okay, so that's the end of our review session. I say this at the beginning of every review session, and it's like, usually I'm lying a little, like usually like, I'm like, guys, I'm just trying to hype you up, but whatever. I promise you, this is real, okay? So last night, I went to sleep really early. I was really tired, and I woke up because I had this crazy dream. It was so vivid. And I woke up, and in the dream, every single one of you took the exam, and you all got awesome scores, and you were all so happy with it. And I woke up because I was just so happy with you guys, and I was like, wow. I don't usually know how to tell the future like this, but this one feels real to me. So with that, good luck. You all are going to do great because I've seen the future and I know it's going to happen. If you guys have any questions, come and Kate and I will stick around to answer any of them. Have a great rest of your day. You can also shoot us emails with any questions. Our emails will be on the course website. And thank you all for coming.
Yay.